Okay, I think it's time for us to start the class. So for the others will come later. Yeah. Okay. Right. Can you see the slide clearly?
No, doctor, we can't see it.
You can't see it.
Can't.
Yeah.
We're still seeing the attendance.
Let me see. Yeah.
No, yeah, we can see the.
Okay. How is it? Okay now.
Yes, doctor. Now we can see it.
Okay. Good. Okay. So let's start the lecture now. We are going to cover lecture 4 and 5, maybe. Okay, for today's lecture, depending on the speed of our lecture. Okay. Right. So for today's lecture, I will emphasize. Sorry. Will be on discrete time signals and its operation. Basically, it is a repetition from what we have learned previously in lecture 2. If you can recall back in lecture 2, we have learned about the continuous time signals and its operations. So we are actually repeating the same thing, but we are now dealing with a discrete time domain, yeah? Okay, so this will be the content of today's lecture, which is a discrete time signals, right? I got a problem now. I cannot move my slide. Okay, then it's okay. Okay. Basically, this is a migration. This slide shows a migration from a continuous time to a discrete time domain in which, based on this diagram, it shows that in order for us to change from continuous time to a discrete time domain, we need to apply two processes. The first one is what we call as a sampling. Yeah, sampling. So sampling is a process of converting a continuous value to a discrete value. Okay, so if we can, if we base on this diagram, okay, so this gray color line basically is the continuous time signal. Okay, so sampling is it is a process whereby we are selecting the point on this particular line, yeah, a point on this particular gray line, yeah. So a process of selecting the point is what we call a sampling, yeah, it's a sampling process. Cool. So basically, you are going to learn this further in communication in third year, topics or subject, a course of principle of communication. We are going to learn about the sampling, the quantization, yeah, which is a process of converting a signal from analog to a digital. Okay, so that's the process, yeah. Okay, so back to this slide, yeah. So we're going to sample the signal according to a certain rule, a sampling theorem rule. Yeah. So once we have selecting, selecting the point or the sampling point there, we have to quantize it. Yeah, we have to quantize. So this is where the quantization process takes place. Yeah, quantization basically is a process of converting a continuous value to a discrete value. Okay, continuous value. For example, if let's say we sample at this particular point, let's say the value is, for instance, let's say 10.5, for example. Yeah, 10.5. So quantization is a process whereby the value of 10.5 shall be now changed to 11. Okay, so we are not changing it to discrete value. So This is the processes that will take place when you want to change or convert from continuous value to a discrete value. Yeah, so it involves sampling and also quantization. Okay. Right. Right. So this is the I can say a repetition again. Okay. Just to show the difference between two type of signal domain. The left hand side is the continuous domain or CT domain where the signals is represented by XT. Okay, we have learned this before. Whereas on the right hand side is your discrete time domain where we represent the signal to be XN. Okay, so a process of converting the signals from continuous to a discrete domain is based on the ADC. ADC stands for analog to digital converter. Yeah, so sampling and quantization is part. Yeah, is part of the component in the ADC. Yeah, so we can see that using the ADC, the XT signal is said to be transformed to the XN. Yeah, and we are getting the XN here. Yeah, where the signals is said to be uh, okay. Let's see. Request to join the class. Let me see. Okay. So a sampling time. Okay. In order for us to change from a continuous time to a discrete time, so this is sampling process take place. Okay. So anyone speaking? Anybody speaking there? Can hear the voice there? Okay. So we have the TS, which is sampling time. Okay, so this is what we have done before. Process a conversion from continuous time to a discrete time. Hello, can you please switch off your microphone? Thank you. Yeah. Okay. So we are now going to learn about the.
Doctor, in the previous slide, can you go back? Yes. What is T, capital T? Not, I'm sorry, N. Well, what is N?
Which one? The N, yeah.
Yes. Is it the equal to T? Like because it's the input or the function of digital or discrete signal.
Okay, basically the TS is sampling time. So T basically is the, I can see this is the number of sample that you're going to have in your signal. Okay, so for instance here, let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 samples there. So T basically is a, I can say, if we compare the continuous time and the discrete time there, so basically T here is a time from this end to this end. Okay, so it is actually similar to the number of samples.
So N will be 11?
You have to count from this point up to this point. Yeah, so the number of samples that you have in your signal.
So yeah, I think the number of points are 11. So if it's 11, hypothetically, N will be 11. TS is the sampling time, whatever it
Yes.
is, right?
Yeah.
Okay, thank you, doctor.
Welcome. Okay. Right. So next we're going to see the type of discrete function. Okay. So basically this is things that we have done before in continuous time signal. If you can recall back that in continuous time we have a step signal and also impulse signal or impulse function. Yeah. In a step signal we have un. Yeah. Un is equals to 1 for all n bigger or equals to 0. And 0 for n less than 0. Yeah, so we can see that based on this diagram, this is the UN in discrete time system. Okay, so 1 for value of n bigger than or equals to 0 and less than 0 equals to 1, equals to 0, sorry, yeah? Right, so that should be the UN, the step function in a discrete time case, yeah? And for the impulse function, we have a delta n, yeah, representation is delta n. Is equals to 1 for the value of n equals to 0 and 0 elsewhere. Okay, so it is represented by this sketching of the function. Yeah, delta n, we have a 1 at n equals to 0 and 0 elsewhere. Okay, so basically this is what we have learned before, right? In continuous time. The difference is on the domain. Yeah, so we have ut for continuous time and you have un for a discrete time. The same things happen for the impulse function. We have a delta t for the continuous time and in discrete time, we have a delta n. Basically, the ideas should be the same, yeah? Okay, so we're going to see the next slide, which is on the arithmetic operations. Okay, so likewise, in the case of continuous time domain, discrete time domain also can be operated. The discrete time domain signal can be operated using the arithmetic operations, the addition, the subtraction, division, and multiplication. Yeah. So I give you examples here, whereby we have two signals labeled as x1n and x2n. Yeah. Okay. So let us try to add the signals, both signals here. So okay. In order for us to add the signals, you must be very careful on the n, yeah? Because the addition or the subtraction or all these arithmetic operations shall involve the processes at respective n value. Okay, for instance, yeah, if you want to add the signals, you have to consider the same n. Yeah, so at n equals to 0, the addition will give us 2, 1 plus 1 is 2. At n equals to 1, it should be 2 plus 2 is 4. Okay. Okay, and for n equals to 2, we have 1 plus 0 will be 1. And for n equals to 3, we have 0 plus 1, which is equals to 1. Okay, so that should be the examples when we add the signals. So the same things apply for the subtraction, okay, the multiplication and also division, yeah? Okay, so you can refer to this slide. Yeah, you can refer to this slide where we have the answers for the addition, division, and multiplication. You can try this on your own. Basically, it's very straightforward, yeah? Just remember that the operations must be done for the same n, yeah? Must be done for the same n. Okay, then. Okay, so next we're going to see the operations that shall be considered for the case of a discrete time signal. We have a time reversal, yeah, somehow same like what we have learned in lecture 2 before, where if we have the xn as the original signals, so the time reversal, or you can also call it as a mirror operation, mathematically it should be returned to be x of negative n. Yeah, x of negative n. Okay, so for instance, if you have this case, yeah, the xn is here, which is having a range from n equals to -1 up to n equals to 3. So when we consider a process of time reversal, so likewise, as what we have learned in continuous time case, the positive end shall be mirrored to the negative side, and the negative end shall be then mirrored to the positive side. So as a result, you have this. Okay, just a folding process, folding operations. Okay, all right. So nothing much to be read here because it's a repeating of what we have done before. Okay, next one is a delay operation or delay case where we have mathematically is given by xn minus nd, and it's a constant, yeah, a constant, shifting constant. Okay, so if we have the xn here, okay, and if we want to, if we add, let's say we shift the signal of xn by -2, let's say we have xn minus 2. So -2 means that it's a shifting process by 2 units to the right. Yeah, 2 units to the right. So as a result, you can see that 0 will be shifted to 2, 1 will be shifted to 3, and 2 will be shifted to 4. Okay, so we can see that this is the case. And if we have xn plus 2, which is the other way around, where the xn signals shall be shifted to the left. Yeah, so we have 0 will be shifted to -2, 1 shall be shifted to -1, and 2 is said to be shifted to 0. Okay, right. So same thing, like what we have learned before. The difference is on the domain. Yeah, the t and the n. That's the only difference. Okay, then this is the exercises that I think we have to do it to ensure that we really understand on these topics of signals operations. Okay, so let's have a look on the solutions for this exercise. Let me share this slide. Okay, so can you see the slide clearly? The solutions clearly?
Yes, doctor, we can see it
Okay,
clearly.
good. Okay, so this is the signals given where we have the x1n, yeah, located at 0 and 1, and the x2n is here, located at -2, -1, and 0 with respective amplitude. Okay, let's have a look at the first question, which is a process of a summation between two signals, where we have x1 of -n plus x2 of n, yeah? Okay, so we know that based on this equation, based on these terms here, x1 -n means the x1 n is said to be reversed. Yeah, it's said to be reversed. So as a result, reversal of x1 n will give us this value. Yeah, will give us this value where the positive n shall be reversed to negative. Yeah, so that's why we have location of your impulse is at -1. Yeah. Okay, so when we add them together between the x1n, x1 -n, and x2n, when we add those signals together, we are supposed to get this. Yeah, so you can try this, yeah, on your own. Okay, number 2, part B. Sorry, number C. Sorry, is part C. You can work on your own on part B. Yeah. Okay, yn is x2 of -n minus 2. So this is a case whereby the x2n is said to experience two operations where we have the time shifting and also the time reversal. Okay, so same case like what we have learned in continuous time. You have to ensure that if we have two operations or two or three operations in which it involves a shifting and a scaling or a reversal, remember that you need to always start with shifting first. Okay, so that is why for the solutions here, what I did is I start with the shifting of -2 or x2 of n minus 2. So what I did is that I'm shifting the signals of x to n by 2 units to the right. So this is the results of a shifting process. Okay, basically we have this x to n. So when we shift it to the right by 2 units, you're going to have these results. Okay, so once we have this, you can proceed further with the reversal of the x to n. Okay, so reversal means that the positive n shall be then folded to negative n, and you get this value or these results. Okay, so that should be the answer for these operations. Yeah. So hopefully you understand this clearly. Yeah, on the operations. Yeah, same like what we have done before in continuous time. Okay, part D, we have additions of two signals where we have x1n plus x2 of negative 2n. Okay, so we have to actually look into the x2n here. Okay, because it involves two operations, which are the scaling of time by 2 and also reversal process. Okay, so what I did is I start with the scaling of time. We have x to n. Okay, we go back to the x to n just now, yeah? X to n is here. Okay, so when we have x2 of 2n, it means that the value of n shall be divided by 2. Yeah, shall be divided by 2. Okay, so 0 divided by 2 will be 0. Negative 1 divided by 2 will be negative half. Negative 2 divided by 2 will be negative 1. Okay, remember that your n must always be an integer. Okay, that is why we have to ignore, we have to omit the value of n at negative half. Okay, so left only with the value of n at 0 and negative 1. Okay, so that's why,
Sir,
yeah.
I didn't understand why we need to ignore the value of -1 and -2.
Okay, I repeat again. This is the case of x to n. So when we have x2 of 2n, a scaling of time, yeah? Scaling of time. So we need to divide the n by 2. Okay, so we are supposed to get 0 divided by 2, which is 0. 1 divided by 2 will be negative half. And negative 2 divided by 2 will be negative 1. Okay, so we are now having n at 0, negative half, and negative 1. And as what we have learned before, the n must always be an integer. It cannot be a decimal value. Yeah, so that is why we are going to omit the value or the signals, the impulse at n equals to negative half due to that reason. Yeah, so you're only left with the signals at 0, which is 2, and also at negative 1, which is 1. Okay, hopefully it's clear. Yeah,
So we remove it, doctor, or
yeah,
we ignore it totally?
yeah,
Even if the amplitude value, for example, if it was 5 or big number,
yes,
we
yes,
ignore
yes.
it because
Mm.
it's the n is not integer,
Yes,
right?
correct, correct.
Okay, thank you very much.
Welcome. Yeah. All right. So now, once we have done with the scaling, we need to proceed with the reversal. So we need to reverse, you need to fold the negative n to the positive side. So we're left with this, and we have to add with the x1n. So these are our x1n initially. So we add them together, we're going to have these signals. Yeah. So this is the addition of the signals. Yeah. Okay, good. Next will be the yn, which is the f is u of negative n plus x1n. Okay, u of negative n is basically it's a step function. Yeah, it is actually a step function of un, which experience a reversal. Okay, so basically un, as what we have learned before, it is having a value of 1 for 0 and value onwards, but 0 for the value of n less than 0. Okay, so the dotted line here means that the value is continuously exists until infinite. Okay, this is dotted line here means. Okay, so when you have a reversal of it, so the positive and all of them shall be now folded to the negative side. So it looks like this. Okay, so now the signal will continuously exist until the negative infinite. Okay, and this will be further added with x1n, which is at 0 and 1. So as a result, when we add them together, these two signals, we're going to have these, yeah? Okay, this is the case, yeah? One amplitude of 1 will be will exist for -1 onwards up to negative infinite. 0 will be 2 due to addition of the signals, and at 1 it will be 1. Okay. Okay, for the H, yeah, this multiplication between two signals where we have the impulse of delta n and x to n. Okay, so we know that the impulse is a straight line of 1 at n equals to 0. This is 1. Multiply with the x to n here. So when we multiply these two signals, we only have a single line at n equals to 0. The rest will be 0, yeah? Right, because it's a multiplication. So because the rest is 0, right? So this value at -2 and -1 of n can be ignored because it will be equal to 0 at the end. Okay, right. For the I, we have again a multiplication between two signals. We have the step function of un multiply with the x2 of n. Okay, so we sketch both signals here. So the un is here, okay, and the x2n is here. So when we multiply those functions, those signals, left only a single line at n equals to 0. Okay, so hopefully you understand why, yeah? Because for this x to n, everything is 0 except at these three locations. Yeah, so when it is multiplied with the un or the step function, okay, so we're going to have a single line at n equals to 0. Okay, and the last example based on that exercises, okay, you have a yn, which is u of -n plus 2 minus, which is subtraction now, the subtraction of x1 of n, x1 of n, yeah. So the un plus 2, so this involves two operations for the step function. We have the shifting of time by +2 and a reversal of time. So we proceed at the first place, shifting by 2 units to the left. Okay, 2 units to the left. So this is the results of the shifting of the step function by 2 units to the left. Okay, so 0 will be then shifted to -2. So we have this case, right? And then the signals shall be reversed because of the reversal process. So all the positive n will be folded to negative, and the negative n will be folded to positive. So we have this case, right? So remember that the n will be continuously exist until negative infinite, yeah, because of the folding process just now. Okay, and this value or this u of -n plus 2 shall be then subtracted with this x1n. Okay, so consider that we have the n at 0 and 1. So subtraction of these two signals will lead to this answer where we have a value of 1, amplitude of 1, for an n of -1 onwards to negative infinite, 0 for n equals to 0 and 1 for n equals to 2. Okay, so this is the solution for exercises that basically you want to ensure, or I want to ensure that you really understand on these operations of the discrete time signal. Okay, is that understood?
Yes, doctor.
Okay, all right, good. Okay, let's proceed with next examples here. This is basically to test your understanding, yeah, on relationship between the step function and also the impulse function. Okay, so this is actually the excerpt from final exam 2015 semester 2. So need to verify, to prove whether these two statements, is it true or false? Okay, so you need to use the graphical representation to justify the answer. So let's have a look at the first one. Okay, okay, this is the case. Where we have a delta n, need to prove whether delta n is it equals to un minus 1, yeah? So basically, we know that un is the signals which look like this, okay, from 0 up to positive infinite. Okay, the rest is 0, yeah? For n less than 0 is 0. While for un minus 1, it's shifting by 1 units to the right. So we have this amplitude for the un minus 1. So when we have a subtraction between the two, it can only show that for all value of n, starting from n equals to 1 up to infinite, the value of n will be 0. Yeah, the value for each n will be 0 because of this subtraction, but left only with a single line, single amplitude at n equals to 0. Yeah, because at n equals to 0, the subtraction will not give any effect. Okay, so it shows that when this subtraction occur, we have a single line at n equals to 0, and as a result, this should be equals to an impulse function of a delta n. So this statement is true. Yeah, this statement that we have here is true. Yeah. Okay, number 2 is to prove that un is equals to summation of delta n minus k from k equals to 0 to infinite. Yeah, we need to prove this. So what we need to do now is that we need to prove it one by one, in which what I did here is I, 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 I put or I insert the value of k one by one. For instance, we start with k equals to 0. So if k equals to 0, we have only a delta n, which is a straight line at n equals to 0 with the amplitude of 1. If k equals to 1, this is the impulse which has been shifted by 1 units to the right. So we have this signal. If k equals to 2, we have a shifting by 2 units to the right. So we have this signal. And if we have k equals to 3, we have a shifting by 3 units to the right. So we have this. And the list follows suit. Yeah, the list follows suit. So which means that if we add them together up to infinite, we can see that there should be a train of impulses. Yeah, a train of impulses starting from 0, 1, 2, 3, 4, and so on. So basically what we have here is a step function. So it is true that the summation of a delta n minus k starting from k equals to 0 to the infinite, the results of the summation for these impulses will give us a step function. So this statement is true, yeah? Okay then, so hopefully you're clear about this example, yeah? Good. Right, so let's have a look at another example. Again, this is dealing with the discrete time signal. This is the excerpt from 2018 for an exam semester 2. We are given a figure question 1c, where we have the input of xn is the input to a system of A. So the xn is basically branch, yeah, said to be branched into two line. The first is going to system of A, yeah, where we have x1n equals to x of 4 minus 2n. This is a new signal of x1n, which is produced from the xn which experience these operations. Okay, so we have x1n as the output of a system of A. The same xn is said to be multiplied by a cn signal, and this will give us the x2n. So at the end here, the output of this system is a summation. I cannot say a summation because it is adder, but the actual case applied here is a subtraction between the x1n and x2n, yeah, because yn is equals to x1n minus the x2n. That should be the case. So the xn is given to be this signal, which is equals to n between -2 and +2 and 0 elsewhere. Okay, yeah? So based on this given figure, you have to determine and sketch these three signals, which are the x1n, which is the output of system A, the x2n, which is the output of multiplier, cn, which is a signal here that involved in the multiplication. If we are given then that the yn, which is the output here, is equals to a 2 delta of n minus 2 minus 2 delta of n minus 3, in which yn consists of two impulses, yeah, at 2 and 3. Okay, yeah, hopefully you clear about the questions posted here, yeah. Right, so let's have a look at the solution for this example. Okay, so this is the figure that been resketched here. Okay, so the xn, if you can recall just now, it is equals to n between -2 and +2 of n. So basically the xn can be drawn or can be sketched to be look like this. Yeah, xn equals to n between -2 and +2. That's why the xn is equals to -2 for n equals to -2, -1 for n equals to -1, 0 for n equals to 0, 1 for n equals to 1, and 2 for n equals to 2. So this is 2, yeah? Amplitude of 2. Right. So now our task is to find out what should be the x1n, yeah? Because this is what requested from the question. So x1n can be obtained if we operate the xn based on these operations, yeah? So it involves three operations where we have a time shifting of 4, we have a scaling of time by 2, and we have a reversal of time, yeah, or middle operations. Okay, so we start with the time shifting. So we shift it by 4 units to the left. Yeah, 4 units to the left. So the xn is said to be shifted by 4 units to the left. So -2 will now move to -6. -1 will move to -5, and so on up to 2, which is then moved to -2. Okay, yeah, so this is the result of shifting by 4 units to the left. And afterwards, we did a reversal process in which all of this negative n shall be then folded to a positive n value. Yeah, so as a result, -2 will now move to +2, -3 will move to +3, and up to -6 will be then moved to +6. Okay, yeah, so this is the result of the folding operations or time reversal operations. And finally, we have a scaling of time where we have to divide all this n value by 2. So when we divide the n by 2, we're going to have 1, 3 over 2, 2, 5 over 2, and 3. So knowing that n must always be an integer, so the value at n equals to 3 over 2 and 5 over 2 can be omitted. So then we only left with the value at n equals to 1, value at n equals to 2, and the value at n equals to 3. So this is the x1n that we have obtained from the operations of xn. Okay. So the x1n can be written mathematically to be two impulses where we have two amplitude of a delta n minus 1. Yeah, impulse of 2 amplitude is shifted by 1 units to the right. And for this, it should be -2 of a delta n minus 3. Yeah, which is a impulse function which has been shifted by 3 units to the right with the amplitude of -2. Okay, so this is the mathematical equations for the x1n. Yeah. Okay, then hopefully you're clear about these issues. Okay, then you need to find out the x2n, right? The x2n, if you can recall back, the x2n is here. Yeah, the x2n is here, in which we know that relationship between the x1n and x2n with the yn is that yn equals to x1n minus x2n. Yeah. Okay, so we have this relationship down here. Okay, this relationship for that two. This is the relationship between the three signals. Yn equals to x1n minus x2n. Yeah. Okay, but before that, we are given in the question that yn equals to 2 delta of n minus 2 minus 2 delta of n minus 3. Okay, so we can sketch the yn to be look like this. Okay, that should be a yn, amplitude of 2 at n equals to 2, amplitude of -2 at n equals to 3. Okay, so based on these equations, yeah, we go back to this equation, we can then calculate, we can then obtain the x2n by simply doing the arithmetic operations between the yn signal and the x1n signal, where the x2n is a subtraction of x1n and yn. Okay, so x1n is here, which is obtained from the first part just now, and we subtract it with the yn here, which is obtained from here. Okay, so when you subtract these two, okay, we are going to have amplitude of 2 at n equals to 1. Okay, at n equals to 2, we have 0 minus 2, it should be negative 2. And at n equals to 3, we have negative 2 minus of negative 2, so it will be 0. So the x to n will be look like this in terms of its sketch. And its representation in mathematics should be returned to be 2 delta function of n minus 1 minus 2 delta function of n minus 2. Okay, so that should be your x to n, yeah? Okay, hopefully you are clear about the solution for this. Okay, so the second questions that is actually, okay, sorry. So we have done with that, yeah? Let me see. Okay, so we have done with the value or sketching and mathematical representation for these three signals, x1n, x2n, and the cn.
What about CN, Doctor?
The cn? Oh,
Yes.
okay. So let me see the cn. Yeah? So the cn is here. So the cn can be calculated by we knowing that the x2n is equals to the x1, the xn multiplied the cn, right? Okay, so the cn can be obtained by simply dividing the x2n and the xn. Okay, so we can refer to the solutions here. So we know that x2n is here, yeah, xn multiplied with cn. So cn basically is a division operation between the x2n and xn. So the x2n is here and the xn is here. So when we divide the two, the division must remember need to be done at respective n value. So we're going to have only two impulses, which is at 1 and 2. The rest will be 0. Okay, so we're going to have 2 divided by 1 will be 2. Negative 2 divided by 2 will be negative 1, which is at n equals to 1 and n equals to 2. So the Cn, the sketch of it should be look like this. And mathematical representation will be 2 delta n minus 1 minus a delta n minus 2. Okay? Right, hopefully you are clear about this solution for this exercise, yeah? Okay, another exercise, another example, which is the excerpt from 2013 semester 1. Consider a signal or a system which look like this. We have the A system. Xt is the continuous time signal. Is said to pass through the ADC, analog to digital converter, the ADC. And the ADC is said to have a sampling period of 1 second. Okay, means that the signal will be sampled for each value of 1 second. Yeah, the signal of xt, this xt will be sampled for each value of 1 second. Okay, that's what meant by a sampling period of 1 second, yeah? Okay, so the result of this sampling will give us the xn, which is a discrete time signal, okay? And the xn is said to be branched into two directions. The first one will be added with the xn, which is said to be delayed by 4 seconds. Okay, so it should be basically based on this box of adder. It should be yn, the output of the adder is xn minus this signal, which is xn minus 4. Yeah, so delay by 4 seconds means xn minus 4, yeah, a delay by 4 seconds. Right, and the yn shall be then multiplied.
Yeah. Doctor, is it delay by 4 seconds or xn delay minus xn minus 4?
Yeah, it should be xn. So xn is here. So when it's delayed by 4 seconds.
Because isn't delay is like shifting?
Yes,
of the
correct.
same.
Correct. So the output here should be xn minus 4, yeah? Okay, xn minus 4. Right. So the output yn shall be multiplied with the n, integer of n, and that will give us the zn, the output of the systems here. Okay, so we are given, based on this question, based on this figure, we are given that xt, this xt, the input is a step function of ut, okay? And we need to sketch what should be the xn, yeah? What should be the xn, okay? That should be the first question. The second one is we need to write the mathematical operation of yn, what should be the yn, and what should be the zn, and we need to plot both functions, yeah? Okay, so let's have a look at the solution for this example. Okay, this is the one. Okay, so we have the xt, which is equals to ut. So when we have a sampling period by 1 second, yeah, so we are supposed to get the xn, which will be equals to un, in which the un should be looked like this, in which the signals shall be sampled by 1 unit. Yeah, so we have a sampling happens at 0, 1, 2, 3, 4, and so on. Let's say the sampling period is 2 seconds. Okay, now it's not 1 second, it's now, let's say, we say the sampling period is 2 seconds, so the sampling will happen at 0, 2, 4, 6, and so on. Okay, right, so you understand the meaning of a sampling period here. 1 second means that for every 1 second, so we assume this is a second unit, yeah, second unit. So we have a 0, 1, 2, 3, 4, and so on, yeah. So the xn is given to be un, which is can be sketched to be look like this, yeah, a step function. Okay, so we need to find out the yn. And as what we have discussed before, the yn is a subtraction between two signals, which is xn minus 4. This is a delay by 4 seconds. Okay, so subtraction of this xn, which is un, and this will be un minus 4. So subtraction between these two signals we will obtain these 4 line or 4 impulses only, which is at 0, n equals to 0, n equals to 1, n equals to 2, and n equals to 3. The rest will be 0 due to this subtraction results, yeah? Okay, I hope you understand. Yeah, because we have discussed this issue from yesterday's problem, okay? So un minus un minus 4 left only with these 4 impulses, yeah, located at respective n values. Okay.
Excuse me, doctor.
Yes.
It's a delay for 4 seconds, right?
Correct.
So isn't xn, or let's say yn, should be xn minus 4 only without subtracting? Like now you want to use the new graph or a new function.
I don't understand your question. What do you mean by that?
Like we only shift the same graph itself or the same equation.
Okay.
We only shift it without subtracting from it.
Okay, I need to share back the question just now, yeah, just to ensure that you really understand the questions, yeah. Okay. This is the case then, yn. Yn is the output, which is a subtraction between those two signals. We have xn here, and here is a delay of the xn itself. So this should be xn minus 4, correct? So yn basically should be the xn minus xn minus 4.
Okay, Doctor. Yeah.
Okay, good. Thank you. Yeah. Okay, then let's proceed with the solutions here. All right. So that should be your yn. And for the zn, if you can recall back the question, it is equals to n of yn. Yeah? So n of yn means that it is multiplication between yn with its n value. So let's say we have this 4 value of yn with respective n value. So for n equals to 0, so we have 0 multiplied with 1, so we have 0. For n equals to 1, we have 1 multiplied with 1, we have 1. For n equals to 2, we have 2 multiplied with 1, we have 2. And for n equals to 3, we have 3 multiplied with 1, so we have 3. So basically, we can write the Zn mathematically to be equals to 3 impulses equation, which is a delta n minus 1 plus 2 delta n minus 2 plus 3 delta n minus 3. Yeah, so you can write this on your own. Yeah. Okay, so I hope you understand that mathematically the Zn can be written in terms of the impulses. Yeah. Okay. All right. Let's have a look at these examples where we have two functions or two systems, yeah, which are the H and G systems. Okay, H is given to be the output is yn, which is equals to x squared of n, where the xn is the input. Yeah, so the system is x squared of n, while for G system, if the input is xn, so the output of yn will be xn minus 1. Yeah. Okay. So for the next part of the question, it states that the systems of H and G are said to be combined, yeah? Said to be combined with the same input, and the output of H and G are said to be added, which will further give us the yn. Okay, right. So based on this condition, based on this condition, we are requested to find the yn, this yn, if the input xn is given by this value. Yeah, given by this value, which is 1, 1, 1, 1, 1. Okay. Okay, bear in mind that if we have these conditions here, the arrow means that this value of 1, yeah, is a value for the n equals to 0. Yeah, it's a value for the n equals to 0, means that the xn will be actually extended, or the range of n, or the range of xn will be from n equals to -2. Okay, this will be for n equals to -2. This is for n equals to -1. This is for n equals to 0. This is for n equals to 1. And this is for n equals to 2. Okay then, yeah. So hopefully you understand the representation for the xn, yeah. So based on that, you are requested to find the yn, yeah. So let's have a look at the solution for this example. Okay, so this is the case of xn. This is the equation for the yn, which is the summation of the output of H and G just now. So the output of H and G, when we combine them together, we add them together, the actual output should be this, which is x squared n plus xn minus 1, yeah? Okay then, so the xn, when we sketch it, it should be look like this, okay? So what we have to do now, since we need to find out the yn, so we need to sketch each of these, yeah, each of these function. We start with x squared of n based on this xn value. So x squared of n, there should be no changes at all because the amplitude is 1 for all n values. So the amplitude will remain as 1. Yeah, so xn will be the same. Okay, and for the xn minus 1, this is a shifting by 1 units to the right. So that's why we have the starting point for the xn minus 1 is at -1 and it will end at 3. Okay, so we need to operate these signals together. So the first signal added with the second signal, but we subtract the third signal. Yeah. Okay, so when we do it, when we do this operation, we are supposed to get the answer which will look like this. So this is your yn, which is a result of the addition and the subtraction of these three signals. Yeah. Yes. Hopefully you can work out on your own. Yeah. The solutions here. Okay then. Hopefully you understand on these examples. Okay, is there any question on this lecture number 4? Okay, we have end lecture number 4, right? So it's still early, it's still 11:56, so I think we need to now proceed with lecture number 5, yeah? So lecture number 5.
Doctor, I have a question in lecture 2. Can I ask it right now or after you finish
Maybe
lecture
you can
5?
ask in your WhatsApp group then, yeah?
Okay, okay, okay.
Okay, thank
Thank
you
you.
very much. Okay, so now we are dealing with lecture number 5. So can you see the slide clearly here? Lecture 5.
There's no
Not yet,
slides,
Doctor.
doctor.
Not yet. Okay, how is it now?
Yes, we
Now
can see.
can.
Okay, thank you very much. Yeah, thank you very much. Okay, lecture 5. So lecture 5 is about the properties of a discrete time system. So basically, we are now talking about the properties of a discrete time. So if you can recall back in lecture number 3, lecture 3, we did learn about the properties of
Doctor, there's a green screen covering the slides.
green screen covering the slide. Let me see. Okay, is it clear?
Yes, doctor, it's clear now.
Okay, good, thank you. Right, basically what we're going to discuss here will be somehow similar to what we have learned in lecture 3 yesterday. If you can recall back yesterday at lecture number 3, we did learn about the properties of continuous time system. Remember, we learned about the properties of causality, stability, time invariant, linearity, and so on, right? Okay, so we are actually repeating the same things, but the emphasis now is towards the discrete time system. But basically, the ideas should be the same. Yeah, ideas should be the same. Okay, let's have a look at this lecture 5. Okay, so these are the things to be learned. We're going to learn about the these four system properties, which is a linearity of the system, time invariant of the system. Going to see about the memory or memoryless of the systems, and also on the causality of the system. Okay, yeah. So basically, this is same like what we have learned yesterday. Yeah. Okay, let's have a look on the linearity property. So the ideas of linearity should be the same as what we have learned yesterday. Okay, in which these are the techniques on testing the system's linearity. Yeah, in which there are two methods. Yeah, to test the system's linearity. The first one is by formulating two inputs, which are x1 and x2n. So the task, the first one is to add the inputs together, and then the input which has been added shall be now being the input to the system, and you got the first output. Yeah, the first output. The second method is we have the input individually, okay, and we excite the system with each input separately. Yeah, separately. So we have the output of the systems due to x1n, and here we have the output of the systems due to x2n, and we add them together, okay, and we have the second output. So you can see that yen is the system's output when the input are said to be added. The second output ybn is the output where the response of the inputs added later, okay, and supposedly if the system is linear, the outputs should be the same. Okay, this is what we have learned yesterday. Same things that we have learned yesterday. Yeah. Okay, so this is the examples to test the linearity of the system, in which your system's equation is this, which is xn squared. Yeah, xn squared. So please don't get confused. Basically, square here is for the x value, x squared of n. Yeah, x squared of n. That should be the right things. Yeah, x squared of n. Okay. So we have two options. The first one is by adding the signals together, and then the addition of the signals which has been added shall be the input to the systems, which is the first case here. So we add the signals together first, x1n plus x2n, and then only we excite the system by this input. So we have the first output shall be this equation, x1n squared plus 2x1n, x2n plus x2n squared. Okay, whereas if we consider the second method, where we consider the response of the input separately. Okay, so we have the second output shall be x1n squared plus x2 squared of n. Okay, so it shows that when we consider these two outputs, both are not the same. Yeah, both are not the same. So we can see that this system is not linear. Okay, is that clear on this uh, technique of testing the system's linearity? Okay, hopefully it's clear. Yeah. Right. This is second case, second examples here, where we have the yn equals to xn plus 2xn minus 1. So your system's equation is this. Yeah, this will be your system equation. We consider the first method where we assume there should be two inputs here, x1n and x2n. Okay, so the first method is we add the inputs together. So by right, for the first case, your yen shall be x1n plus x2n, okay, in which we substitute the sinus addition into this xn, okay, plus 2x1n minus 1 plus x. So this is supposed to be x2, yeah, sorry. This is supposed to be x2, please correct this for me. X1n minus 1 plus x2n minus 1, okay? So the results for this summation will give us this equation down here. And if we consider the second case, whereby we consider the response for each input individually, and then only we add the output, or then only we add the responses. So we are supposed to get x1n, sorry, yeah, x1n plus 2x1n minus 1 plus x2n plus 2x2n minus 1. Okay, so it shows that if we compare these two outputs, YA and YB, both are the same. So this system is a linear system. Okay, so the system is linear. All right. So let's have a look at this example number 3, where we want to consider, we want to test the system's linearity. Yeah, we want to test the system linearity. Okay, this is basically same question as what we have seen in lecture 4 before. Yeah, basically this is part 2 of the question, in which you have to determine the linearity properties of the system Yn in this figure. Okay, yeah, so we have the input xn, the Yn is just a summation of the response of h and g. Okay, so Yn basically is x squared n plus xn minus xn minus 1. Same like what we have in the previous examples, yeah? Okay, so let's proceed with testing the system's linearity. This is linearity. Okay, so let's have a look at the solution for this problem. Let me see. Okay, this is the one. Okay, now we have that Yn is equals to x squared of n plus xn minus xn minus 1, yeah? So as what we have learned, in order for us to test the linearity of the system, first thing first, you need to assume two inputs, which are x1 and x2n, yeah? x1n and x2n, yeah? So we have to assume this. So the first method is we add the inputs together, yeah? We add the inputs together, then we get the response. So this is the first case, nah? The inputs are said to be added together. So we have the input to the system is x1n plus x2n. Okay, and the system equation is this. So we need to represent, or we need to substitute the x1n plus x2n into these equations. Okay, so we are supposed to get yn is x1n plus x2n squared, okay, which is a substitution of the first terms there, plus substitution of the second terms, which is x1n plus x2n, minus the third terms, which is x1n minus 1 plus x2n minus 1. Okay, yeah? Right, so what I did here, I just want to repeat again that I substitute for each n of these terms, each xn of these is substituted by x1n plus x2n. Okay, so we have these terms, and end up we have this equation of yn, the first output, yeah, the first output. So please work out for the yn. So supposedly you will be having this yn value, yeah, for the first case. Okay, for the second case, or second method, is that we induced the input, or we excite the input individually to the system. So x1n is excited to the system, x2n is then excited to the system. So the responses of this system's output, the responses from the systems will be then added. Okay, yeah? Okay, for examples, if we consider first case, the first input of x1n to the system, so we are supposed to get the output will be x1n squared plus x1n minus x1n minus 1. Okay, for the second input x2n, when it passed through the system, the response of the system will be x2n squared plus x2n minus x2n minus 1. So the yn is just a summation of these responses. So we have output number 2. Okay, so once we have done this, we have to compare the first input and the second output. So it shows that first output and the second output are not the same. So based on this, we can see that the system that we are having in the question is not linear. Okay, it's not linear. Okay, hopefully you are clear about the solutions, yeah? So I'm hoping that by now you have understand how to test the system linearity for both cases of continuous time and discrete time systems, yeah? Because the method are the same. Okay, next one is the system, is the time invariant of the system. Okay, this is what we have learned yesterday, that the shifting at the input will result in the same shifting value at the output. Okay, this is a time invariant system, yeah? I repeat again, a time invariant system is a case whereby a shifting at the input signals, a shifting for the output signals, will result in the same shifting for the output signals, yeah? Okay, that should be the time invariant system. Okay, let's have a look at these examples here, yeah, a very simple example. We have the equation of the system here, yn equals to half of xn plus xn minus 1. Okay, so if we delay the input by nd, yeah, if we delay the input by nd, supposedly the resultant equation will be half xn minus nd plus xn, so this should be only one minus, yeah, not two minus, one minus only. So please cancel one minus of it. Should be a plus xn minus 1 minus nd, yeah? Okay, this is the case where we delay the input by nd. So let's try to delay the output by nd. So when we delay the output by nd, we have to consider these equations up here. So when we delay the output by nd, so substitute n by n minus d. So we are supposed to get half xn minus nd plus xn minus nd minus 1, which shows that the second equation and the third equations are the same, which means that delaying the input by nd will result in the same delaying constant by nd for the output. So the system that we have here, this yn system, is a time invariant system, yeah? Okay, so let's have a look at this example here. This is an excerpt from test 1, 2018 semester 2. Determine whether the yn is equals to xn negative n plus xn minus 4. Whether this system that we have here, is it time invariant system or time varying system? Okay, so you have to test this, yeah? You have to test whether the system, is it time invariant or time variant? So let's have a look at the solution for this. Yeah. So basically, you can just base on this, lah. Yeah. Let's say we delay the input first. Yeah. We delay the input first. Xn minus k. Yeah. Xn minus k. If we delay the input xn minus k, we are supposed to get the results for this system equation shall be x minus n minus k, yeah, minus n minus k, we delay by k, yeah. So it's supposed to be x minus n minus k plus x n minus 4 minus k. Okay, that should be the case where we delay the input by k unit. But when we delay the output by k unit, which is y n minus k, so we have to substitute this n by n minus k, this n by n minus k, and this n by n minus k. So we can see that when we delay the output by k, the equations here becomes negative in a bracket of n minus k. So the resultant will be negative n plus k. Yeah, negative n plus k. And this will be xn minus 4 minus k, which shows that when we delay the input by k unit, the answer for this delaying equation will not be the same if we delay the output by k unit. So the system that we have here is a time-varying system. It's time-varying system, yeah. So let me see if I have a solution for this. Yeah, I have it here. Yeah, you can just double check it here. Then, yeah. Let's say we delay the input by k. So what we have done here is we delay the input by k unit. So we are supposed to get this equation number one. And the second case, if we delay the output by k unit, yeah, you are supposed to get this case, yeah, and out we're going to have negative n plus k and so on. So it shows that number one and number two are not the same. So these systems that we have is a time varying system. Yeah, it's time varying system. Yeah. Okay. Next is a causality. So same things that we have learned yesterday. A system is causal if the output at any time depends only on the input at the present time and in the past. Yeah, so that's what we call a causal system. And I mentioned yesterday that all real-time physical system is causal. Yeah, all real physical systems are causal because the output will only depends on the present input and past input. Yeah, no such case that we can depends on the future input. Yeah. Right, so n is a current value, n minus k is past values, and n plus k are future values. Yeah. Okay, so hopefully you understand the causality properties. Okay, for example, the example state that yn is given by this. So we can say that based on this yn, the system that we have here is causal because from the equations here, there is no future values. So yn is a causal system. Likewise, for this particular case, yn is alpha n minus 1 un. So we can say that based on this yn, the output will only depends on current value and past values. So again, the system that we have here is a causal system. And for the third case here, we have yn summation of xn minus k, okay, x minus k, where we have k range from -2 to +1. So when we substituted the k from -2 to +1, we can have this yn. So we can say that yn is depending on n plus 1 and n plus 2, which are a future values. So we can see that yn is not causal. Okay, all right. All right, then. So system memory is same like what we have learned yesterday. Yeah, memory is that it can recall, it can store the values other than its present values. Yeah, so that we call a memory system. So discussion shall be the same as what we have learned yesterday. So I won't repeating the same things here. Okay, so let's have a look at these examples here, which is a excerpt from 2015 semester 2. Okay, so we have these signals of xn. Yeah, xn is having amplitude of 4 at n equals to 0. negative 4 at n equals to 1, 0 at n equals to 2, and 4 at n equals to 3. Okay, so xn is said to be branched into two different branches. The first one is xn delayed by 2 seconds, which produce the yn. The xn, the other xn is then branch to the adder. So basically this adder is a process of adding the yn with the xn, and the results of this addition will be multiplied with 5, which is the amplifier, multiplied with 5, and that will give us the zn. Yeah. Okay, so hopefully you understand the system's case, yeah, the system's flow, and also the xn signals. What you have to do is that you have, number one, you have to write the expression for xn and yn. Okay, and the expression basically involves the sum of discrete impulse functions. So this is the hint, yeah? The second sentence basically is a hint in which the expression for both xn and yn shall be a discrete impulse function. Okay. Number two, you have to sketch the output Zn. And number three, you have to determine whether the signal Zn here, is it causal or non-causal, or is it has memory or memoryless. Okay. So you have to justify the answer. So these are the questions related to the systems and the signal of Xn. Yeah. So let's have a look at the solution for this problem. Okay. Okay. So we have this Xn just now. Okay. You as what requested from the question, you need to write the equation for both xn and yn in terms of impulse functions. So we know that based on this given xn, it should be written to be 4 of delta n, because we have impulses at 0, negative 1 and 3. So it should be 4 delta n minus 4 delta n minus 1 plus 4 delta n minus 3. Okay. And for the yn, so knowing that yn is the output of a delay box here, so delayed by 2 seconds means that yn is xn minus 2. Yeah, so xn minus 2 means that you have to delete the xn. So as a result, it is same if we delay this value here. So we're going to have 4 of delta n minus 2 minus 4 delta n minus 3 plus 4 delta n minus 5. Yeah, so we delaying these xn functions by 2 units or 2 seconds. Yeah? Okay, so that should be the xn and the yn. Any question on this? No, yeah? Okay, so let's proceed further. The solutions. Need to find out the Zn, yeah, based on the question. So we know that from the figure just now, okay, from this figure, the Zn is a multiplication of 5, the amplifier, with the output of adder, in which Zn is 5 multiplied with yn plus xn. So basically, equation should be look like this. Okay, so we have 5 multiplied by this yn and xn, in which yn and xn have been obtained from this part just now. Yeah. So please work out for this summation. So we are supposed to get yeah. So we are supposed to get 4 impulses here. Yeah, because 4 delta n minus 3 here can be cancelled out. Yeah, can be cancelled out. So we left only with delta n minus 1, delta n minus 2, and delta n minus 5. Yeah. So end up we're going to have 4 impulses with the amplitude of 20 for n equals to 0, negative 20 for n equals to 1, positive 20 for n equals to 2, and positive 20 for n equals to 5. Okay, so based on this equation, we can see that the output of Zn will be depending on the input at the present time and also on the previous value, right? Past value. So we can see that Zn, or the system that we are considering now, is a system which has memory. yeah, which has memory because it can recall, it can store the input from the previous values. And also the system is said to be causal. Because why? Because the output is said to be depending on the present input and the past input values. There is no case where it depends on the future input value. So due to this, the system is causal and the system is said to have memory, to have memory. Okay then?
Doctor,
Yeah.
can I ask why the inverse is 20?
Let me see. Sorry, yeah. Okay. Again, why?
It's 20 here at the end, at the result.
The results. Because it's a multiplication, right? Yn plus xn will give us
That's a
4.
memory of
4, right?
outputs.
So if we base on the systems
The text
diagram, this amplifier, you have to multiply with 5. Multiply with 5. Multiply with 5. So it's amplifier. So you have to multiply.
Has memory.
You have to multiply the addition of the signals with 5. So that's why we have a 20 as the output amplitude. Okay then?
Okay, thank you, Doctor.
Welcome. Okay, so this is second examples, but I won't be doing these examples. I hope that you can do it on your own, but the solution for this will be given upon request. Yeah, I can give you a solution because I've done it, but I want you to test this on your own, yeah, before I give you the solutions, yeah. So please try this on your own to test your understanding on this issue, whether you able to distinguish or determine whether the system that we have here, the system of E that we have here, is it a system with memory, a system which is time invariant or not, or a system which is linear or not. Yeah, so you have to test the systems of A on these three properties. Okay, so try these exercises on your own. If you get any problems, if you face any problem, you can always get back to me then. Okay. All right. So with that, we have end up lecture 5, and that should be the end of chapter 1. Okay. So to wrap up, just to summarize chapter 1. So chapter 1, we have learned about the signals, basic signals in terms of its operations, in terms of the basic functions, and also the system properties for both cases of continuous time domain and discrete time domain. Okay, right. Lecture 6 will be on convolution. I won't be covering this lecture 6, but I will provide you with the slides of lecture 6 in the classroom, Google Classroom. Okay, so you have to learn this on your own. You have to discuss this with your colleagues. Yeah, because convolution topics will be tested in your assignment. Yeah. Right. So next week, inshallah, on Sunday, we are going to proceed with chapter 2, which will be which we start on the topics of Fourier series. Okay then. Is there any questions before we end the class today?
Doctor, can we ask questions about previous lecture? To be exact, lecture 2.
Lecture 2, you can discuss is in the WhatsApp, yeah?
Yeah, but it takes time to answer the questions.
No, but it's okay. We can add this in the WhatsApp group. Okay? All right. Okay, thank you very much, Bunkai, for your response. I believe that there should be no questions from the students, yeah? So this meeting, this lecture is I record the lectures, so I will give you the copy of this recording, yeah, and maybe I put it in the YouTube channel then. Okay, since there is no questions, thank you very much. Yeah, so we're going to end the class now. So hope to see you again next Sunday, yeah, at 11 o'clock. Okay, have a nice day ahead. Have a nice weekend ahead, yeah. Thank you very much. Yeah, see you next time. Thank you.